Good morning. So this is going to be the lesson on these types of word. Really, it's just potential energy is the main topic here, but it's going to be the words electric potential energy, electric potential without the word energy, and electric potential, the difference of them, electric potential difference. Generally, in circuits, you see kind of this word here. And then this is really closely associated to gravity potential energy. So you'll see throughout this lesson, I'm going to show the gravity example, and then I'm going to go on and show the electricity example, because it's very confusing stuff, but I find if you relate it to gravity itself, it's very similar, so you can kind of relate it and understand it a little better. So let's start off with what we learned last day. Recall E is called the field strength in the units newtons per coulomb for electricity. Okay, so and it's newtons per kilogram for gravity. Okay, so you have this E here. They find that E is the electricity field strength of force per charge, or Newton per coulomb. And the charge that they're talking about is they have kind of a big source charge, so that I denote QS, and then they have a tiny test charge, and I call that QT. If you think of that as like the Earth and a satellite going around, QS is the Earth's charge, and QT is kind of the satellite's charge. So here, E is the force of the charge over the charge of the test charge. And it can also be, if you substitute Coulomb's law in for F, it can be K times the source charge divided by the distance between them squared. So that's another way to get the same number for your E. So it's either the force that's applied in the test charge or the source charge and the distance between them. So that's what we did last day. And then if we look at the gravity version of it, E is the same thing, Fg, not force charge, but force of gravity, divided by the mass of 1, which is the satellite. So if we have the satellite out here, you have your mass of your Earth, and you have your mass of your satellite, or M1. Then it's Fg over M1. And if you substitute Newton's universal law in for there, you get the constant G times the mass of the Earth divided by r squared. So it's really the same thing. One thing to note is that this is acceleration when it comes to gravity, but when it comes to statics, it's not. It's force per charge. Or the force per charge of the test there. And then this one is also force per mass, if you want to relate it, per mass. Alright, so now on to the kind of the new stuff is potential energy. So this is the word. We've learned potential energy is mgh for gravity, or if you want to get more specific, G is not just G, but G is that formula where you can go PE is, I'm going to have to look at the formula sheet. Alright. But it was negative G M1 M2 over R was our potential energy for gravity, kind of the more complicated one. Okay, that's when you substitute kind of the Fg, the Newton's gravitational universal gravitational law for G, then you'll end up getting this. But besides the fact, that's what we've done so far. And one thing that we've remembered with this equation is when you're infinity distance away, potential energy was 0. And when you were right in the center of the Earth, potential energy was negative infinity. Okay? So as you get closer to Earth, it goes more and more negative. That's kind of the idea with potential energy for gravity. Okay, so now let's look at statics. We have positive and negative. So there's two different examples. It's what happens when your satellite and your source charge are the same charge, or what happens when this is one charge, this is the opposite charge. So case one. So if you have two charges that attract, it will be the same as gravity. So the same as this one here. The highest potential energy is 0 at an infinity point away. So an example here is charges that attract. The example here is just like gravity. Say this one's positive and say this one's a negative. If we have a point over here, let's say infinity distance, way over here, then potential energy here is 0, and then as you get closer and closer to the center, potential energy is negative infinity. Okay, and the way you can think of this is it's going to have more potential energy the further away it is, because then it'll have the potential to fall towards the Earth or towards the charge more because it's attracted. So that's the idea there. Now let's go to case 2. Two same charges. Here if you have the same charge, the closer they are together, the more potential energy they have. So it's kind of opposite. Here the more potential energy, but here if you have, these are showing the same charge. Let's pretend this one's a positive and this one's a positive as well. Okay, so here you can picture if the positive gets closer to the positive, it'll have more potential to fly away. Versus if it's further away, it'll have less potential. So here, how it works is potential energy is still 0 at an infinity point away. But at the positive charge, it's no longer going to be negative infinity, but potential energy gets greater. It goes to positive infinity. And it all works out when you use the equation. You don't have to worry about this too much. You should get the right values, just plugging in the appropriate signs. All right. So those are the two cases, 1, 2. So if we look, our equation for potential energy is the same as normal. So potential energy is mass times gravity times height. But in our case, since we're dealing with statics, instead of mass, it's charge. Instead of gravity, or acceleration of gravity, it's going to be the electric field. And instead of height, it's just going to be the distance between the two things. Okay, but it's the same thing essentially. And since E is G, mass of the Earth over R squared, or in statics case, K times the charge over R squared, we can plug that in there and we can get this here. K, the charge of the test, the charge of the source over R. So that's what potential energy is. This is the equation that you want to use most of the time in the questions. Okay, so if they're opposite charge, then one's going to be positive, one's going to be negative. If they're the same charge, they're either both going to be positive or both going to be negative, which makes this overall positive. Okay, so it ends up working out. That's how you get potential energy. It's the distance between them and their charges with the K constant. All right, so let's try a practice question. So here's some just pictures to help show it. But what is the electric potential energy relative to infinity is what it says, because infinity point away it's 0, of an electron in a hydrogen atom if the electron is 5 e to the negative 11 meters from the proton. So one thing to note here is on your formula sheet, on the back side of it, you have elementary charge. That's the charge of every proton and every electron. So the proton, electron have a charge of 1.602 e to the negative 19 coulomb. So very small charge relative to a coulomb. So I like to draw a picture always. You have infinity point, you have your source charge, and then you have your test charge here. Okay, somewhere in between. You have a distance r between them, and in this case the proton is the source charge because the electron is the one that's moving relative. So this one's going to be the negative charge, and r is going to be 5 e to the negative 11 meters. So potential energy is 0. Since they're the same, as you get closer you lose potential energy. So potential energy is 0 over there. So it's saying, what is the electric potential energy if the electron is this close to the proton? Okay, so we just use our formula. PE is K, the test charge, the source charge, and the distance between them. So we're going to use our K value, which is 8.988 e to the 9, test charge, which is this, but it's negative because it's an electron. And then another one of this, but it's positive because of the proton, and the distance between them, which is 5 e to the minus 11. We plug that all into our calculator and we get negative 4.61 e to the negative 18. And what unit do I put on? It's potential energy, so it has to be a joule. So a very small amount of potential energy. For something like that, it's probably because they're so close to one another and there's not much more space to go. Only a very tiny portion of a meter left to go. Okay, question 2. How far apart are two electrons if the potential energy to bring one of the electrons from infinity is that? Okay, so this time you have your source charge, which is an electron, you have your test charge, which is an electron, you have your infinity point away, where potential energy is 0. So this case is opposite. This has potential energy of infinity if you get them close to one another, but as you go further you lose potential energy. So here potential energy is K QT QS over R, which is going to be our K constant, which we know what that is. And then this time it's still 1.602 for the electron, but it's negative e to the negative 19, and I'm going to go squared because that's what the QS is as well. And then the distance between them, we don't know. And our potential energy, they say, is the 9.45 e to the negative 20. So now we got to solve for our R. So we're going to multiply and divide by that. And overall, when we do that and calculate it, we get 2.44 e to the negative 9 meters. Okay, so it has to be really close together to have a potential energy of that many joules, which is a very small amount of joules. A lot smaller than 1. Alright, so there's some potential energy questions. Now on to the next section. We have this next word, which looks like electric potential energy, but this time it's called electric potential. So this can be very confusing because the words are so similar, but pretty much is electric potential energy when you divide by charge. Okay, so it is electric potential energy divided by charge. That's what it is. But let's just try to understand it. Let's recall gravity, which is potential energy of mgh. If someone is sitting 50 kilograms, 2.04 meter ledge, they would have 1,000 joules. You can calculate it, but it's 1,000 joules of potential energy in respect to the surface. So if we divide by the mass of the person, divide by that 50 kilograms, or go PE divided by M1, we get 20 joules per kilogram of person at a 2.04 spot. Okay, so that is the gravity potential of this person or of any person at that spot, 20 joules per kilogram of person. So the 1,000 joules is relative to this person, 1,000 joules of energy for that person is the electric potential energy. But if we divide by its mass, we can get how much for any person? 20 joules per kilogram of person. Okay, so that's the gravity potential. Now if we look at electric potential, it's the same idea. PE, potential energy, is charge times the electric field, which is the same as gravity. Not the same as gravity, but the same idea as gravity, and the distance between them. Then we divide by the charge of the test charge to get potential energy per charge. Okay, so and here we would get the number of joules per coulomb of charge. So instead of joules per kilogram, we're getting joules per coulomb of the test charge at that particular spot. Okay, so if we divide by this charge, we can get really the number of joules for any charge, right? Because we have it per charge, so we kind of have the basic unit. This is what we call a volt. You've all heard of a volt before. Batteries have them. So a battery is 9 volts. What that means is 9 joules per coulomb of charge that flows through. So you get 9 joules of work per coulomb that flows through a battery. But overall, volts is potential energy over the test charge, or per test charge of, I guess, of a charge from a source charge. And if you plug in potential energy equation here, you end up getting K, the source charge, over R. So you can either use this one or you can use this one. Okay, you can use this one if you don't get the test charge, because really the volt doesn't matter on what the test charge is. It just matters how much the source charge is and how far away you are from it. So this means that electric potential is fully dependent on location and the size of your source charge. So overall, this would be the one I would highlight next. All right. So if we look at this, this would be an example of a test charge here. This would be an example of a source charge here. One thing to note is a volt uses variable V. That's the variable it uses. And it uses the unit V. So it's not normally do things do that. Like mass uses variable M, and unit kilograms, this uses variable V, and unit volt, which is a V as well. Okay. So here's a sample problem. A charge of 4e to the negative 13 coulombs is moved between two charged parallel plates. So generally, if you have two parallel plates, you make one negative, one positive, and it makes the electrical field, the E, the same everywhere in between. But that doesn't really work for potential energy. It's different at different spots for potential energy. This increases the potential energy in a charge by 7.3 e to the negative 15 joules. What is the electric potential between the two plates? Okay, so here I'm going to go use our equation here. V is PE over QT. I know I have the charge of the test charge, and I know I have potential energy here, so I know I'm going to have to use this equation. So it's going to be 7.3 e to the negative 15 joules, and then 4 e to the negative 13 coulombs, and this is going to get me 0.018 volts. Okay, so V is equal to 0.018 volts. But the spot that it's in relative to these two plates must give it, another way to write it is 0.018 joules per coulomb, because that's what a volt is. Gives you 0.018 joules per coulomb that passes through. Alright, here's another practice question. How much energy does an electron have if it has an electric potential of 50 volts? Okay, so here we can go the same equation, PE over QT. So here we know that our electron charge is 1.602 e to the negative 19 by looking on our formula sheet on the back. And then we can solve for potential energy, how much energy does it have? Yeah, so we're going to multiply by QT, and we're going to get PE equals V times QT. And our voltage is 50 volts. It's kind of hard to understand what a volt really is, but again, it's kind of the spot of the potential energy divided by the coulombs. And then charge is 1.602 e to the negative 19 coulombs. And then this is going to give you 8.01 e to the negative 18 joules, which is a very small amount of work done. But you have a very small amount of charge there, so that kind of makes sense. One thing to note is with your answers, it's hard to decide if they actually make sense in this unit because they're all crazy small amounts or crazy big amounts, so it's very hard to decide sometimes. Okay, question 5. What is the electric potential relative to infinity at a distance of 0.9 meters from a point charge of 50 microcoulombs or negative 50 microcoulombs? So it's saying a point charge, so that's a positive charge generally. A test charge is generally positive. 0.9 meters from this. It's saying what is the voltage here, right there. That's what the question's asking. Because voltage, remember, is electric potential. Okay, so let's do number 1. What happens if that's positive 50 microcoulombs? We know that the other equation that we can use is KQS over R, because we don't have the charge of whatever's over here, but we don't need it. We just need the source charge divided by the distance of them. So we can do the constant K times 50 e to the negative 6 over 0.90 meters, and we get 499,333 volts, which is around 500,000 volts or joules per coulomb. So in that spot, every coulomb that passes through, you get 500,000 joules of energy. Question 2. What happens if you have a negative 50? That's a negative charge. Okay. So here, one thing to note here is per coulomb of charge, if you want to bring to infinity to this spot, it takes 500,000 joules. That's kind of what it means. So you have your infinity spot way out there. To bring something from here to here, it takes 500,000 joules of energy. That's because your thing is positively charged and it's going relatively close to this. It has to go a lot of distance or a lot of energy. So here, if we do the negative version, it's KQS over R, and then it's K times negative 50 e to the negative 6 over 0.90. So pretty much the same equation. We get negative 499,333 volts, which is around negative 500,000 volts or joules per coulomb. So here you have, in this example, it's going to be negative. We got to go 0.9 meters, and it wants to know the voltage here. So really, it's from the relative to infinity point. So to go from infinity to this point here, which is 0.9 meters from this, how much energy is it going to take? It says negative 500,000 joules per coulomb. So what does that really mean? It really means you're from a spot of zero potential energy, and you really don't have to put in any work. It'll go straight there on its own because it's attracted. This is a positive test charge. It's attracted to the negative, so it's going to go down. And when it reaches this point, you have kind of gained 500,000 joules. Okay? Here you have to put in 500,000 joules to bring two like charges close together. But this, if they're oppositely charged, it's really you're going to gain it, or you're not going to have to do anything. All right. The last topic here is, let's recall gravity. If you wanted to move something from so this is called electric potential difference. What it really is just the same thing as volts, what we just learned, but it's the difference between two spots. Okay, so it's usually V2 minus V1 is the change in volts. Okay, so electric potential difference just has that triangle. It just means if you subtract two electric potentials from each other, from two spots. Okay, so let's recall gravity. If you wanted to move something from that 2.04 meter ledge to a higher ledge of 4.49 meters ledge, you would have to go from 1,000 joules of potential energy at this spot to a 2,200 joule spot of 4.49 meters. Okay, in respect to joules per coulomb, you would need to go 20 joules per coulomb on the first spot to 44 joules per per kilogram of ledge. Okay, so this is gravity potential is what it's talking about here, which is similar to electric potential. The difference here, if you take the difference of the two spots, is 24 joules per kilogram of item, is called the gravity potential difference, read as you need to perform 24 joules of work per kilogram of your object to get from spot 1 to spot 2. Spot 1 to spot 2. Okay? This time, the reason why they do per kilogram, they don't leave it in potential energy, is because then they can use any object at all. So then if you have like a 10,000 kilogram object, you just times your 24 by 10,000, and then you'll have how much potential energy. So it kind of is an easier unit to work with when you want to work with any object. So in respect to electricity, it's the same thing. The change in voltage, or the electric potential difference, is just the electric potential, and the triangle means change in, or the difference, or when you go one minus the other. Okay, so here delta PE just means PE at spot 2, potential energy at spot 2 minus potential energy at spot 1. Okay, so it's really just our equation from volts, but they add in the triangle, which just means you calculate it twice at the two spots and you minus them. Okay, so remember, this can be also V2 minus V1. So if we substitute our potential energy equation in here, we can get this, which you might not use too often, but we're going to keep it there. The main part will be that there. But it's K, QS, the source charge, over the distance at spot 1, the distance at spot 2, times the distance at spot 2 minus the distance at spot 1. Okay? And then we have over here just a little thing. Delta V can also be represented as this, but you don't use that too often. That's why it's so small. So here we go, the work you need to perform to get delta V, joules of work per coulomb charge of object to get from spot 1 to spot 2. Where R2 is the distance from the source charge in the second spot, and the distance from the source charge in the first spot is R1. Okay, so let's look at these sample problems. How much work is needed to get 1 e to the negative 6 coulombs of positive charge between 2 points where the potential difference is 12 volts? Okay, so that means 12 joules per coulomb is the amount of work you need to get from spot 1 to spot 2. Okay, so spot 1, we're going to move to spot 2, and it's going to take 12 joules per coulomb. Okay, so it's going to be a positive charge. So since you're putting in work, you're going to guess that the source charge, wherever it is going to be positive as well. Okay, because you're going to have to put in work to get it closer to the positive charge. All right, so now let's use our equation. Delta V is equal to delta PE over the charge of the test, okay, which is this. So here we're looking for, we have voltage, we have the electric potential difference, so we just need to find out how much work, which is the same as energy. So let's solve for delta PE. And then this is going to be equal to 12 times 1 e to the negative 6, which is 1.2 e to the negative 5 joules of energy you're going to need to get from spot 1 to spot 2. All right, very abstract concepts. What is the energy stored in a 9-volt battery if the total charge transferred from one set of electrodes to the other is 4e to the 5 coulombs, which is a huge amount of coulombs. Normally we deal with negative exponents. This is not negative, so it's a huge amount of coulombs. So let's use our equation. Delta V is delta PE over QT. We solve for potential energy. What is the energy stored in the battery? If you have your test charge and you have your voltage, which is 9 volts, which is the amount of joules per coulomb of energy that you need to bring from one spot to another spot. So again, it's going to be delta PE is delta V times QT, which is going to be 9 times 4e to the 5, which is going to be 3,600,000 joules. All right, so that's the lesson. Thank you.